Hello students. Now, after completing the Doppler effect in light and the two cases where you get the red shift and violet shift understanding, we will move towards the next topic, which is symmetric nature of Doppler effect in light. Again, a very interesting part. So earlier we had seen that when the source of light, okay, and the observer are moving along the same direction, the apparent frequency or the observed frequency of light observed by the observer is given by C minus CO upon C minus CS into N. Correct? Now with this, to show the symmetric nature, we will study two cases. Okay? So out of which, case number 1. So case number 1 will say that the source is moving towards the stationary observer with speed u. Okay, so definitely we'll have what as per the diagram is the job first. So I'll show c velocity of light in this case. Fine. So over here I have my source. Okay, and here is the observer. Fine. What we said, the source is moving towards the stationary observer, so we can very well write first CO is equal to 0. Fine. Source is moving towards observer, so arrow is towards here with velocity u. Clear? So in the formula which I just showed you about the source is moving, source and the observer are moving along the same direction, that formula I'll write and I'll do the necessary changes. Changes means what? As CO is stationary now, so we'll write N dash is C upon C minus CS is U into N. Fine. So my formula will be, over here I'll write, formula is N dash is equal to C divided by C minus U. Why? Because CS is equal to U. CS is equal to U. Correct? So now with this into N. Now this formula means what? We get N dash to be greater than N, which means the source is moving towards the stationary observer, there is increase in the apparent frequency. Now this equation I can simplify and write in such a way by taking C common. So what we'll write, N dash is equal to C common numerator, C common denominator. What will happen over here? This is 1 upon 1 minus U by C into N. Cancel the C. Correct? What we get? N dash is equal to 1 minus U by C raised to minus 1 times N. Correct? Now, as you know that the value of CS or U is very less than C. Correct? So using the binomial expression, I get the expression N dash is equal to 1 plus U by C, because this is minus, this is minus. So 1 plus U by C into N. Correct? This is the answer what I got for my apparent frequency for the case 1 where the observer is stationary and the source is moving towards the observer. I got this relation. Now case number 2 shows that the observer is moving towards the stationary source with velocity u. Velocity is same, that's what we meant earlier also. Okay? So here again the diagram. First is C, source is over here, observer is over here. Okay? This is S, this is O. Now what we said, that the source is stationary. So I'll say very clearly CS is 0. And the observer is moving towards the source. So arrow is very critical with a velocity u. Fine. So we substitute this value in this expression. C minus U upon C minus CS. Okay. So what is my CO? CO is U. And what is my CS? CS is 0. So I'll get the expression N dash is equal to C minus of minus, and CO value is U, so minus U. Okay, sorry, my arrow is different, so minus of minus U, so I'll have to make it plus U. Okay, C plus U divided by C. So you mention over here as CO is equal to minus U. Reason behind the arrow is towards the source, not away from the source. Okay, so C plus U by C into N. Clear? Now with the same logic, take C common. So what will happen? C in the numerator, C in the denominator. What I'll get? 1 plus, okay, U by C. Nothing much complication. Raised to N. Okay, so 1 plus U by C. Here also what I got? 1 plus U by C into N. So here I don't have to even use the binomial. So this is my expression. Cancel C. So here I can say N dash is equal to 1 plus U by C into N. So from this expression 1 and expression number 2, what I get? Okay, one more thing I can do. Here I mentioned N dash, so here I'll make it N double dash because everything is similar. Okay, so N double dash, N double dash. So here we can conclude and say confidently from equation number 1 and equation number 2 that the expression for N dash is similar to N double dash, which means what? Let the source move towards the observer, keeping observer stationary, or let the source stationary, observer move towards the source. In both the cases, the value of apparent frequency, okay, is apparent frequency expression is 1 plus U by C into N. 1 plus U by C into N. So N dash greater than N is valid for both the cases. So what we can see? The equality. We want to show symmetric nature. So what we can say? The equality of two apparent frequency N dash and N double dash under the same relative motion condition. Okay, the Doppler effect in light will be termed as symmetric nature. Okay, Doppler effect in light as symmetric nature. That's what we have seen with the simple example. Okay, now the next topic is again very interesting, which is the applications. Already we knew few, already we discussed, so we'll just revise it in some time. So here what I have, applications of Doppler effect. So the first one, what is the first one? Is radar. Everybody has heard this word radar. So what is this radar stands for? Radar stands for radio range detecting. RA is over here, detecting and ranging. So D, okay, and ranging. Okay, radio detecting and ranging is basically used, okay, to do what? To detect and monitor various objects. Okay, now where what is the principle over here? Principle definitely is the principle of Doppler effect. So what do they do here to locate the object? Okay, what they do is a beam of radio wave actually, okay, given out from the system get reflected from the moving object, either in the aeroplane or even underwater. Aeroplane, automobile, which is in the path of the beam. So if the beam detects that object, what will they do? These reflected waves are received by the system. So the reflected wave will have different frequency than the emitted wave. So these two waves will produce beats. Okay, so this is basically they are used the principle of Doppler effect by showing as we have explained it or studied it earlier. Okay, so where it is used basically? So radio waves move through the air at a constant speed. Okay, so the radar device can calculate how far the object is located. Okay, so it is based on how long it takes the radio signal to return by detecting the object. Okay, so radio speed traps are used in defense system basically, or even in police department they use this system to calculate the speed of vehicle. When they mention on highways that you need to travel on this lane by 80 speed or 120 speed or whatever, you need to follow that. If they do not follow, they get to know by this system. Once they get to know, they can definitely fire you or tell you that you have made a crime and you need to pay for that, because when it is mentioned to drive on 80 speed, you are driving by the speed of 120 or whatever higher than that. So this is the best thing which they can detect at what speed the car has moved by violating the rule. This is the first application. Second application already we discussed, which is called as red shift. Now I explained you what is the red shift means earlier. Okay, now in this case what we can say, that our universe is composed of many stars and galaxies. Okay, so if we observe the spectrum of light from a distant star or galaxy, there will be apparent change in frequency due to motion of star or galaxy. Okay, now what we have studied earlier, if the star is moving, we said over here suppose there is a source and here is the observer. Okay, so if the star is moving away from the observer who is on the earth, okay, and if we take spectrum of light from the moving star superimposed on the stationary spectrum produced, what we observe, that the spectral line corresponding to the star will shift towards the red end of the stationary spectrum. This is basically called as the red shift. Okay, so when the red shift is observed, what happens basically, the star is moving away from the observer. So this is suppose my source and this is the observer. The diagram is like this. This is C, this is S, this is O. The observer is stationary, fine, and the star is moving away from the observer like this. Now who was the scientist first who observed this? It was a Hubble. So you must have heard the word Hubble's telescope. Okay, so Hubble was the scientist, American astronomer. He observed that light waves from a distant galaxies were shifted so much to the red side of the spectrum that they must be moving away from the Milky Way. Okay, the galaxy in which Earth is located at a very high rate. So at the same time, what happens basically, the nearer galaxies experience much less of the red shift as this phenomenon came to be known. Okay, meaning that they were moving away at a relatively lower speed. So if I say that you must have heard the word bubble, same way you must have heard the word Big Bang Theory. Okay, there are many series going on television. So if you are not watched, whenever you have time, you do watch. There is a lot of understanding, a lot of knowledge also you get with some web series or some normal serials. Okay, so this is basically the biggest application of redshift. Now the third one also we are aware of it, which is the blue shift or the violet shift, which we have just finished explanation few minutes back. So here what happens, if the star, this is my star and this is the observer. Okay, so if the star is moving towards the observer is where? On the earth. The spectral line of the spectrum of star, which is superimposed on the stationary spectrum produced in the laboratory, shifts towards the blue end of the spectrum. This is blue shift, as simple as possible. So when the star is moving towards the earth, we get a blue shift, and when the star is moving towards the earth, okay, and when the star is moving away from the earth, red shift. That's what we can remember. Now the fourth application is speed. Whose speed? Speed of distant stars. This is also an important work. How to measure which star is at what distance from earth. That is again a very technical issue. So here what do the astronomers do? Astronomers use these words to describe changes in the wavelengths of the radio waves or X-rays. Okay, so what basically they do? They feel that the relative motion is entirely along the line of sight. Okay, then the Doppler shift of light formula is what? Delta lambda divided by lambda is minus v by c. Okay, now over here, what is lambda? Basically is the wavelength emitted by the source. What is delta lambda? Difference between lambda and wavelength measured by the observer. What is c? Obviously velocity of light. And what is v? Is the relative speed of the observer and the source in the line of sight. Okay, so this variable v is counted as positive if the velocity is one of recession and negative if it is one of approach. Okay, so if you solve this equation, okay, for the velocity, what we'll get? We'll get v is equal to c into delta lambda by lambda. Okay, so we can use Doppler effect equation to calculate the radial velocity of an object. Okay, so if you know three things: the speed of light, the original wavelength, okay, and the difference between the wavelength, then it's not difficult for us to find out the value of relative speed. Okay, this is my fourth application. We'll move towards the next one, which is rotational speed of a binary star. Now, as the word binary is definitely, they are talking about the two stars together. So what is this? Basically, about around 50% of stars do not exist on their own like sun. Okay, but in fact they observed in pairs called the binary systems. Now means what? Some stars exist in three stars also, but binary stars orbit a common center of mass. So which means what? I'll draw it over here and show you. Suppose I say that this is the diagram. Okay, I should have drawn little bigger. I'll draw it here again. So suppose this is okay, and somewhere over here I will show the center of mass. Okay, and I'll join with the line. So I'll draw one star over here, other star over here, and this will be my center of mass or C. Fine. So what do they say? That binary star orbit a common center of mass. So now with the more massive star orbiting closer to the center of mass, okay, and by making observations of the Doppler shift in the spectra, we are able to deduce or find out the information about the star's mass and speed. Now these days we know every star's mass, the speed at which they are moving and whatnot. Okay, so a binary star system consists of a pair of stars orbiting about their center of mass. Okay, and by measuring the Doppler shifts of both stars as a function of time, one can determine the orbital period, the radial velocity of each star. If the observer is located in the orbital plane, the orbital radii can be found for both the stars. Okay, the orbital radii and the Kepler's third law determine the total mass of the system. Okay, the next application, which is application number 6, is nothing but width of the spectral line. Width of the spectral line. Now what is spectral line? A spectral line in the spectrum of light from discharge tube containing gas does not appear as a sharp line of certain frequency. You always observe there is some band, okay, so that it will have definitely it not appear in a sharp line of certain frequency. It has small but finite band, finite width, okay. So one of the reason for this observed width of this thing is definitely Doppler effect in light, okay. So for this we have a formula to find out the half width of the spectral line. So the formula is half width is equal to W is equal to frequency nu into under root T by A. So obviously W is half width. This nu is the frequency. Either I can use N or nu. Okay. T is the temperature and A is the atomic weight of the gas. So knowing half width of the spectral line, suppose I know this, I know frequency, I know atomic weight, I can very easily get the temperature of the gas which can be calculated. Okay. So a spectral line emitted by an atom has finite width, and there are three distinct physical processes which contribute to this broadening. Okay. So once we know one parameter, other will not be difficult for you to get it. So these are all basically 6 applications, out of which everybody knows about radar, how to detect a object on their path. Red shift, violet, blue shift already we had discussed in the earlier topics. Okay. Then comes the speed of distant star, okay, where they are located. We have a formula. Then rotational speed of a binary star. Binary stars I mentioned always occur in pair. So with the center of mass, it is easy for us to know, okay, to get what is called as the rotational speed of them, and the last will be width of spectral line, and the formula is given over here. Okay. So with this 6 applications and symmetric nature of Doppler effect in light or Doppler effect in light itself, okay, this completes our theory part of the last chapter of your syllabus of paper 1. Now what is left only is the problems, which I'll take it in just 1 or 2 days. Okay. Just go through this notes. Anything not clear, feel free to ask. Okay. Thank you very much. These are very simple ones, how to get n dash and whatnot. But just go through it. Anything not clear, feel free to ask. I'll take it the problems in few days time. Okay. Thank you very much.